Okay, so today we're going to look at arc length, and the basic idea is this question: how can we find the length of a curve y equal to f of x from x equals a to x equals to b? So if we have some smooth curve like this, the problem is if I start over here with x equals to a and I end over here with x equal to b, what's my length? Well, we're going to go through the same three steps that we've seen for any of the applications. We find some way of approximating it, we find some way of systematically improving the accuracy of the approximation, and then we can use a limit to bridge the gap between our approximation and the actual value. So that is the idea, and so the first thing is to figure out a way of approximating that smooth curve's length. So let's get rid of this one, and we're going to actually go take a look at Desmos. Here we have this red curve, we want to approximate its length. So the way we're going to do that is just using a straight line. We know how to find the length of a straight line, and so here I could use the length of this blue line to be approximately the length of our smooth curve. Fine, it's clearly not a very good approximation, but it'll do. And then the second thing we want to do is systematically improve the accuracy of that approximation. So how do we do that? Well, the same way we did with Riemann sums, is that we can sort of increase the number of line segments here. So if I just even go up to n equal to 2, so now I'm using two different points, two different line segments to approximate the length of the red curve, and I can do that again. I could use n equal to 3, I could use n equal to 4, and we notice that the more line segments that we use, the more accurately our straight lines sort of stick to the smooth curve, and so you can imagine here that our approximation is going to become more and more accurate. Now here, the third step, now that we know how to systematically improve the accuracy of our approximation, the last step is just to take a limit. We can take a limit here as the number of line segments goes to infinity, and what that's going to look like is something like this. Here as we go through n equal to 7, 8, and so on, you could see that our approximation just gets better and better as the number of line segments goes to infinity. You can imagine that we're going to get exactly the arc length of that smooth curve. It will no longer be just an approximation. So let's stop it here at 20 line segments, and you can hardly tell the difference between our approximation at this zoom level and the actual curve itself. So let's go back and take a look at our notes. So this is very much what we're working with. Okay, if I wanted to know what my length here of this curve is going to be, we're going to be doing an approximation using a certain number of points and a certain number of line segments, and that's going to form our approximation. So here, what we're going to do is we're going to sort of zoom in on one of these situations. So if we do that, what we end up with, if we sort of exaggerate it, is going to be our curve coming in like this. We have here, let's say, this is going to be pi minus 1, and let's call this pi. So those are 2 points that we have, and then we have our red line joining the two of them. That's our straight line. And what we want to do is figure out the length of that red line. Well, that's not too bad. All we have to do here is set up the Pythagorean theorem. We have our right angle triangle, and we know that here the length of our base is going to be our change in x between the 2 points, and the height is going to be our delta y. So what does that mean then? If I take a look here at the hypotenuse, let's call that delta s, then we can say delta s is going to be the square root of delta x squared plus delta y squared. Okay, fine. So now that we know how to find the length of those red segments, we also know that if we add them up, we get an approximation to the total arc length. So here, the total arc length, let's call it L. That's going to be approximated by adding up all of these delta s's, okay, starting with the first one over here, okay, and then ending off with n being the number of line segments that we are using. So fine, we can add these all up, each one having an individual length like this. And we can increase the number of line segments that we're using. We can increase n to increase the accuracy of our approximation, but we know specifically that if we want to get the exact value of arc length, what we're going to do is take the limit as the number of line segments, n, goes to infinity, and that's the limit here of this square root. So fine, except that our goal here is to actually set this up as a definite integral, and we are missing really one main thing for our definite integral. It's usually that we have limit as x, or rather, limit as n goes to infinity, sum from 1 to n, f of xi delta x. So even if this plays the role of f of xi, what we are missing very much is multiplication here by delta x. So we need to do a little bit of algebra to fix that. Let's get rid of all of this. And really, to get that delta x outside, we're going to look at factoring a delta x from inside right here. Now you might say to yourself that this term doesn't have a delta x, and you're right, so the algebra is just going to be a little bit wonky, but it will still work out. So if we factor out that delta x, let's see what we're left with. So inside the square root, remember I want it to be delta x once I take it outside of the square root. So I'm going to actually be factoring out a delta x squared inside. And if I factor delta x squared from the first term, which is delta x squared already, then I'm left with 1. And if I factor delta x squared from the second term, which is delta y squared, I end up with delta y squared divided by delta x squared. And so it's definitely going to sort of look like we've made this a lot worse, but we wanted this term right here. We wanted that delta x squared term. Now we have it. If I take the square root, I can take it outside, and really we end up now with just a square root 1 plus, let's simplify this a little bit as well, so it's 1 plus delta y over delta x. This whole thing will be squared. Now what we have outside is delta x. So pretty much we are now ready to convert this into a definite integral. We have our integrand, and we are integrating with respect to x. So perfect, we end up with the definite integral. We are integrating this square root, which we remember as n goes to infinity. That's the same as delta x going to 0, which means that our delta y over delta x, that's going to become our derivative of the function. That's going to become y prime, or simply dy dx. So we can put that here. We have dy dx squared. We are integrating with respect to x, and we have our smallest x value. We started our curve at x equal to a, and we finished our curve at x equal to b. And that right there, that is the arc length formula. Okay, so we end up getting arc length is equal to integral a to b square root 1 plus, here you can just put y prime, you could put f prime of x. Let's put f prime of x squared dx. Okay, And that's going to be the rule. That's going to be your arc length rule moving forward. Okay, so a lot of the difficulty in these arc length questions, it's not going to come from remembering the formula. It's going to come from, first of all, calculating f prime. You have to make sure you don't mess up your chain rule, don't mess up your derivatives. And then we're going to be squaring it. Okay, and if you think about it, the process of taking the derivative and squaring it, okay, and then adding 1 and taking the square root, doing all of this all together makes a very potentially complicated function. And afterwards, unfortunately, we have to integrate that function. So that whole process is where the difficulty comes for these arc length problems. And that's it.